Welcome to video 9 on the TTb course. This video is from part 2 of the TTb course. In part 2, from video 3 to video 10, we consider various fundamental techniques that form the foundation of reliable TT systems. In this video, we consider the creation of TT systems that involve more than one processor. We'll start by considering designs in which the schedulers on the different processors are synchronized. We'll then consider GALS designs. These are globally asynchronous, locally synchronous options. So in a GALS design, different parts of the system are synchronized internally, but the overall system need not be fully synchronous. The material in this video is based on Chapter 9 in the ERES2 book. If you've not yet read Chapter 9 in the book, I suggest you stop the video, read Chapter 9 and come back to the video after you've completed this reading. So we're going to look at both fully synchronous and GALS designs in this video. Let's consider some basic material that's required when we work with multiple processors in a design. Multiprocessor designs are very common in automotive, aerospace, medical, industrial automation, fire systems, intruder alarms, etc. Some of these designs are distributed. For example, we might use a CAN bus to hook together processors at different ends of a vehicle or different ends of a factory. And some are local. We might use multiple processors on the same printed circuit board to support design challenges such as SIL or ASO decomposition. We'll look at both of these options later in this course. So we might need to consider multiprocessor designs that are distributed, possibly some distance apart, and multiprocessor designs which are local, where we have multiple processors on the same PCB. Here's an example of a distributed design, a test bed for an industrial automation system. We might have means of measuring temperature, means of controlling a system, and actuator systems. So inputs, system processing, actuators on a typical industrial automation system. We might have a local design where we use multiple processors arranged on the same PCB, in this case as part of the control system for an electric vehicle. Two possible options for designs that involve multiple processors. Sometimes the system may be fully synchronized, so we might have a situation in which we have the scheduler on here synchronized with the scheduler on here and synchronized with the scheduler on here. That's a fully synchronized solution. Alternatively, in the kind of designs we might consider on this course, this microcontroller might run a scheduler. These two microcontrollers, MCU A, MCU B, may run another scheduler. The activities on MCU A and MCU B might be synchronized. The schedulers on MCU A and MCU B might be synchronized, but the schedulers on MCU I and the scheduler on MCU A may not be synchronized. This would be a globally asynchronous, locally synchronous design. That is, this design is this component is TT, this component is TT, but these two components are not synchronized together. This is a globally asynchronous, locally synchronous design option. We'll consider both options in this video. Let's start with the fully synchronous design option. Suppose we want to take two or more processors and we want to synchronize the activity on those two different processors. These are three key challenges that we face. We need to synchronize the clocks on the different nodes. We need to share data between the different nodes, and we need to detect and manage node and connection failures. So I'm using node here to refer generally to a particular microcontroller. So let's assume we want to synchronize the clocks on the different microcontrollers, we want to share data between the different microcontrollers, and we want to detect and manage failures in each microcontroller and in the connections between the microcontrollers. Let's start by synchronizing the clocks on our different nodes in the system. If I take a set of microcontrollers and oscillators from a particular factory, I go and pick up these oscillator components. At the end of the production line, I pick 3 oscillator components off the end of the production line at the same time, hook them onto these microcontrollers. There's no links between the microcontrollers. Let's say I connect a heartbeat LED to each microcontroller, run identical code in each microcontroller, go off, have lunch, come back. The heartbeat LEDs will not be flashing at exactly the same time. There'll be some differences in the oscillator frequencies, and my various processors will not be synchronized. So we'll see drift between the processors. That drift will become more extreme if, for example, we run these different microcontrollers with their oscillators at slightly different temperatures. Then we will see even greater drift in the oscillator frequencies. And we will see greater drift in the activities on the different processors. Synchronization matters. Suppose that we're going to assist this surgeon by creating a robotic system to support surgery. And we're going to use this robotic system to perform brain surgery. If the different parts of this system, for example, the different motors that control the arms of these robots, if these are not perfectly synchronized, then, and we start to do a cutting operation into my brain, if the robot arms are not completely synchronized, then we won't be able to control precisely where the cuts occur, depth and position of the cuts in this kind of design. And the system simply won't operate correctly. Synchronization between the processors in many designs is a crucial requirement. Build our system in this way. The bus that we're using here to communicate between our master and our slave nodes cannot be used for other purposes in most systems. We need exclusive access to this bus, otherwise we won't be able to guarantee that the messages will get through when we require them to get through. That will result in a very high level of jitter in our system. So we're sending alternate tick messages and acknowledgement messages, tick messages and acknowledgement messages over the system. One slave replies at a time, and all the communication is directed via the master node in this particular configuration of a shared clock design. If we want to detect errors from the master's perspective, the master can detect that the slave is not operational because it doesn't receive an acknowledgement message. So if I send a message to slave 1 and I don't receive an acknowledgement message back, I can conclude that the network is damaged or that slave 1 is not operating correctly. From the slave perspective, the slave can detect that the master is not operating if it doesn't receive a tick message for longer than the expected tick interval. So if a tick message is not received in an interval greater than the tick period, the slave can assume that there's a fault in the master node or in the network link. So if we detect faults and we want to handle them on the master, the simplest thing the master can do is to enter a safe state and shut down the network. So this is easy to implement and is effective in most systems. So all we do if we detect a fault anywhere in the system is that we shut the system down. And if the master thinks that one of the slaves is faulty, the master stops sending out any tick messages on the bus. All of the tick messages, all of the slaves detect that no tick messages have been sent. All of the slave nodes will enter a fail-safe state, and the whole network will be shut down. Another option is if the master detects a problem, it can try to restart the network. It takes time to restart the network. Incorrect implementation can be more dangerous, and this is a more challenging option to achieve. It can be done, and it can be done very effectively, but it's more complicated to achieve this than simply entering a fail-safe state. Sometimes what we can do is if a particular slave does not respond, the master can engage a backup slave in the system. The code again is a little more complicated to implement, but this can also be done effectively in our design. The simplest way of detecting faults on the slave is to use a watchdog timer. So if we've got tick messages coming over the bus every 10 milliseconds, say, we would incorporate a watchdog timer on the slave with a timeout interval of 11 milliseconds perhaps. If the slave does not receive a message from the master within before the watchdog timer overflows, then the watchdog timer will reset the slave and typically will force the slave to enter a fail-safe state. Slave nodes can enter this state. They may then keep listening for tick messages, or they may simply remain permanently in the fail-safe state. Let's consider how we can implement a shared clock network using CAN. Very briefly, CAN is a controller area network protocol. It's popular and cost-effective due to its simplicity, its low cost, its availability, and its robustness. We can support comparatively high-speed communications, 1 megabit per second over short distances, and low-speed communications over very long distances up to about 10 kilometers. A large number of microcontrollers have on-chip support for CAN, allowing the protocol to be used with minimal overheads. If you must do so, there are off-chip CAN transceivers available, so you can use this protocol with virtually any device. In theory, the maximum number of nodes on a CAN bus is 32, but some more modern designs allow a larger number of nodes to be used. Messages in CAN can be up to 8 bytes in length. Using the kind of protocols that we're discussing in this course, we typically allow us to use 7 data bytes per tick, and we use 1 byte to identify the slave node that we're trying to communicate with. CAN is a shared broadcast bus. All messages are sent to all nodes. However, each message has an identifier. This can be used to filter the messages. This means that by using a full CAN controller, we can ensure that a particular node will only respond to relevant messages, that is, messages with a particular ID. This is very powerful. What this means in practice, for example, is that a slave node can be set to ignore all messages that are directed from a different slave to the master. In other words, the slave node will only respond to the tick messages that are addressed to it, and the slave mode, so any other messages that are sent on the bus won't generate an interrupt on a particular slave. If we have we look at the number of bits in a CAN message, you can look up the details via Google or through some other source, but we have 154 bits per message in a CAN message typically. We require 2 messages per tick to do the simple protocol we've been talking about so far. So to allow 1 tick message to be sent on the bus and 1 acknowledgement message to be sent on the bus from a single slave, and to do both of these within 1 tick, then we require a baud rate of at least 308,000 baud. If we use 350 K baud, this gives a margin for error and allows for some overheads, and we can achieve this with CAN at distances up to around 100 meters. If you need longer distances, the tick interval must either be increased or we need to add repeater nodes to the bus at about 100 meter intervals. So with a bit rate of about 350 kilobaud, then we can achieve 1 millisecond ticks using a shared clock designed on a CAN bus. We can also use shared clock schedulers on local systems, that is, systems that are based on the same PCB. So here we might have 2 microcontrollers, MCU A and MCU B, in a shared clock arrangement on the same printed circuit board. So here we might have a serial communication link to a PLC with 1 link, and we might have a second link between the microcontrollers also using serial comms. We've looked at this example before. So we might use, for example, a UART-based communication link with a DMA support to allow us to send 100-byte messages between MCU A and MCU B, for example, and the arrival of each 100-byte messages on MCU B would drive the scheduler on this node. Sometimes the failure of the COM bus can be a useful way of determining what's happening with this. A shared clock arrangement like this, then we can detect variations in the oscillator frequency between these 2 microcontrollers of approximately 2%. If we only have a single processor and we're using an RC oscillator as a benchmark, then we may not be able to detect variations in the oscillator frequency of much less than 50%. This is one reason why duplicated designs involving a couple of processors with cross-checks are popular in safety-critical systems. Now let's consider GALS designs. GALS stands for Globally Asynchronous, Locally Synchronous. This example shows an emergency shutdown system. So we might have MCUI running a standard TTC scheduler. As we've discussed in the last few slides, we might have MCU A and MCU B in a duplicator arrangement running a shared clock scheduler to synchronize the activity on MCU A and MCU B. If this is a GALS design, then there's no direct synchronization between MCU I and MCU A. So this is not a shared clock scheduler. MCU I and MCU A in a GALS design won't be running a shared clock scheduler. However, MCU A and MCU B may be running a shared clock scheduler. So in this example, we have a GALS arrangement. In this design, MCUI is responsible for reading and checking a switch, S1, We'll assume this is the emergency stop input. If this switch is pressed, a message will be sent on what we assume is a UART-based communication link to MCU-A. This is not a synchronous message transfer. The MCU-A and MCU-B are, we're going to assume, involved in various activities relating to monitoring the control system in this case. One of these activities involves monitoring the emergency stop input. In order to ensure reliable operation, MCU-A and MCU-B work together and are linked to form a shared clock network. So this is again a duplicator platform. In this way, MCU-I and MCU-AB are locally synchronous, while the overall system design is asynchronous, because the two modules are not synchronized with one another. This is a common architecture in many systems, particularly those in which a customer may assemble a system such as a factory control system or a vehicle based on components that are obtained from different suppliers. In video 12, we'll revisit this design and demonstrate that it is possible to determine precisely how long it will take to start to shut down the control system after switch S1 is pressed. So we'll demonstrate that we can model both fully time-triggered designs and GALS time-triggered designs in video 12. That brings us to the end of this video. Please read Chapter 10 in the ERES2 book before you watch the next video. Thank you for watching.